Okay, in this screencast we're going to go over how to get started on the shell lab. So the first thing you're going to want to do is make sure that you've pulled all the most recent changes in the Git repository. I've already done that, so I can go ahead and make my shell. I already made it once before, so I'm going to do a make clean followed by a make. And you'll see the first line, the first GCC invocation here, builds the actual tiny shell, the TSH binary. The following 4 lines build a couple of other binaries that are used in testing your tiny shell, and we'll talk about those in a little bit. So you can go ahead and run the tiny shell now with /tsh, and it brings up a prompt, and at this point you can also type in commands or try to type in commands. You'll find that nothing actually does anything. Quit also doesn't quit the shell. You can, though, quit the shell by using Control-D. And this is kind of nice. It's because the shell understands the end of file marker, which is sent when you hit Control-D on Unix. So you can quit out of your shell. And you're going to want to remember that for when you try to implement quit, but maybe you've broken it or you've broken something else. Another binary you'll find in the directory is /ref. And this is the reference shell. What you're going to be doing for the most part in this lab is trying to get your own shell to mimic the behavior of the reference shell. You can run the reference shell by doing /tsh-ref. And this brings up the reference shell. Notice that the reference shell does process commands such as quit. Let me start it up again. And it'll also run commands for which you type in the proper and full path. So again, that works. And notice typing in binls produces the output for binls followed by the shell prompt, which means that it's a foreground command. And if we type bin ps, that lists the processes that are currently running. And notice that /ref is the shell, ps is the program that's currently running, but all the processes that were run previously are no longer showing up, which means that we've properly disposed of them. The shell has reaped them. Okay. Now, while we're looking at the reference shell, I'd like to point out a few features of shells and some features you're going to have to implement. So the first feature, which isn't really a feature, is simply running foreground commands. And again, you can run ls, ps, you can run ls with arguments. Okay. And this is the most basic behavior of a shell. Now, it's also possible to run commands in the background. Now, to run a meaningful command in the background, first let's take a look at what myspin does. Remember, that's one of the provided binaries. If I give it a number, such as 3, myspin will sit there for 3 seconds not doing anything. And that clearly shows that the shell is waiting for that process to finish, or that job to finish, before giving me back my prompt. So if I were to put an ampersand after myspin3, what happens at that point is the shell runs that process, well, creates a new process that runs that command in the background. And that command executes in the background while I'm given my prompt back. So I can do that again. Let's give it a longer runtime this time, though. Let's give it something like 10. Run it in the background. Notice I get my prompt back immediately. And if I follow that up with a built-in command jobs, which lists the jobs that are currently running, it tells me, hey, in the background there is this process running the myspin10 command with a PID of 3963 with a job ID of 1, and it's currently running in the background. Now that 10 seconds at least has gone by and I type jobs, that job is now gone. I can create multiple background jobs. So let's create one there. Let's do another one there. And typing jobs shows me that there are now 2 background jobs running simultaneously. One of them is still left, and soon enough, let's give it a moment, that one's completed too. Now, another neat thing I can do with background jobs, so let's say I've backgrounded this process that runs myspin10. After it's in the background, I can also put it in the foreground by using the fg built-in command. And fg takes as an argument the job ID preceded by a % of the job that I want to put in the foreground. And notice what that did was it took the myspin10 that I put in the background and made it run in the foreground again. So it behaved very much like a foreground, well, exactly like a foreground process. Notice if I do bin ps at this point, I have no zombie processes, which is to say the shell has been all along properly reaping background processes. Okay, Another thing that my shell should be able to process is a so-called stop signal. And I send a stop signal to a foreground process while it's running by hitting Control Z. Notice the shell tells me that this process with PID 4030 corresponding to job 1 has been stopped by signal 20, which is the SIG stop signal, which I issued by hitting Control Z. Okay. If I type jobs, it'll tell me that there's a stopped process. Now, what I can do at this point is I can either take that process and run it in the background or bring it back and run it in the foreground. Let's go ahead and do the latter first. So I'll run it in the foreground by doing FG%1, and this does two things. It takes the process, continues it by sending it a SIG CONT, a SIG cont, and it also places it in the foreground, allowing it to run to completion, if I do let it, which I will. Another thing I can do is if I run the same process this time in the foreground, and I hit Control Z to stop it, I can also send it a SIG cont using the built-in BG command, but this time running in the background. And notice it's running in the background because I put it in the background. And I'll give it a little bit of time to complete. Typing jobs should demonstrate it's gone. Again, let me verify that there are no zombie processes. And that's the reference shell. Let's talk about trace files now. So while you can drop into TSH or tshell ref, the reference shell, to test out behavior and see if you've gotten things right, the best way of testing your shell and making sure that you're actually going about things incrementally and in a modular way is to use the trace files. So if you look at your directory listing, you'll see trace01.txt all the way up through trace20.txt. Each of these trace files is meant to test a specific piece of your shell implementation. And we can go ahead and run these trace files by using make test01, which runs your own implementation TSH through the paces of trace01.txt. And we can try that. And notice that tests to see if your shell terminates correctly on end of file. Turns out that the given implementation already terminates properly on end of file, so it does work. Now we can also see how the reference shell behaves for that test. And to do that, we type rtest01, meaning let's try this trace out on the reference shell. So if I type that, of course, we would expect the reference shell to work correctly, and it does. Now let me try the reference shell on trace2, which I do with make rtest02, and that trace apparently checks to see if the shell processes the built-in command correctly, in this case the quit command. And it does. And let's try it with our own shell, which we haven't touched yet. And notice, unfortunately, that it doesn't seem to be working correctly. Okay, it doesn't because I haven't made any modifications to it to have it handle the built-in quit command yet. And unfortunately, it's just sitting there hanging, and so I'm going to have to force it to quit, and I can use Control C for that. Okay, now we could go on, but clearly I'm going to have to get it so it processes quit correctly before I can proceed. Now I can go ahead and try my reference shell out with some of the more advanced traces. So let's try rtest3, let's try 4, let's try 5. And notice that each of these traces tests sort of ever more advanced features or advanced functionality within the reference shell and correspondingly in your own shell. So your workflow is pretty much going to be, let's try reference shell trace, or let's try one of the traces on the reference shell. And again, you're going to sort of want to work incrementally. So start with trace 1, 2, 3, 4, etc. See how the reference shell behaves. And after you've looked at its output, for example, if we've hit trace 5, this is what the reference shell produces as output. What you're going to want to do is have your own shell mimic this output. Of course, not by just printing things out to mimic it, but so that its behavior is correct as per this output. You're going to want to make your shell, again, produce the same output. Okay, and that's generally your workflow, is going to be checking to see what the reference shell does and then trying to get your own shell to do the same thing. Okay, so let's go ahead and get started with a shell. I want to write a little bit of code so you can see how to get started working on the shell. So the shell's implementation is going to be found entirely in tsh.c. And the first thing you're going to want to do is go to the top and edit the names and emails lines. And they're plural, but of course this is an individual assignment. And enter your own information. So I'll do that right now. Whoops. Okay, so now that I've done that, we're ready to start making some changes to the shell implementation. The first thing we're going to want to do is just scroll down, and we're not going to look at this in too much detail, but I want to point out that the most important part, at least the first thing that you're going to want to work on, is the eval function. And the eval function is called from main, right here. Let me set line numbers so we can see line numbers. At line 153, currently at least, inside our shell's read eval loop. And notice that eval is called with a command line that basically we obtain from the user by using this fgetS. Okay, so line 145 is where we actually read the command line. So you don't have to change any of this. This stuff is pre-written and it works perfectly fine. Notice at the same line, or I should say at line 147, is where the tiny shell checks to see if the standard input currently is at the end of file or not. And if it is, then we exit the shell. And that's why it currently handles the end of file condition properly. So eval clearly is what we want to work on. So scrolling down to eval again. Notice it's currently blank. Okay, and the first thing we're going to want to do is take the command line and parse it into its component parts. The first part of the command line, usually, unless it's a built-in command, is going to be the path to the command we want to execute, and the remainder is going to consist of command line arguments for that command. So to do the parsing, turns out we already have a pre-written function. It's called parseLine, and parseLine takes as its first argument a command line, and its second argument a pointer to a pointer called argv, which it's going to populate with pointers, this makes sense, to individual tokens within the command line string. Okay, so in eval, in other words, we're going to have to declare this argv array that we're going to hand over to parseLine. And the argv array is going to consist of an array of pointers to characters, so that those pointers can get populated by parseLine, like I just described. So here's a declaration that'll suffice. So I'm going to create an array of characters to pointers, and the trick really is just going to be deciding how big this is going to be. And it turns out that there's a max args constant already defined in the file up top. I'm not going to scroll there, but you can look for it yourself. That defines the maximum number of arguments for a given command. So we'll just go ahead and use that. And we're ready to call parseLine. Before calling it though, and we would call it with command line and argv, you'll see in a second. Before calling it, we have to check out the return type of parseLine, see what it returns. Notice it returns an integer. And the integer return type, in this case, is used to describe, let's read the comment here, it says return true if the user has requested a background job, false if the user has requested a foreground job. So we're going to have to keep track of that information. So let's just say, okay, so let's keep track of the return value of parseLine. And let's pass it our command line. And let's pass it our argv, which is going to get populated. And boom, we should have a parsed command line. After parsing the command line, we're going to want to do a couple of things. Well, on the one hand, if it's an actual command, not a built-in command, we're going to want to fork and exec a child process. On the other hand, if it is a built-in command, we're going to want to carry out the built-in command and not try and create a child process. Now, we want to do this in a modular way, and it turns out if we scroll past parseLine, you'll see that there's a built-in command function that's supposed to check to see if the user's typing a built-in command, and if so, execute it immediately. So let's go ahead and try and take care of the quit built-in command, because that's the easiest. Okay, so we'll assume that built-in command gets called correctly. So let's work on built-in command first. Built-in command takes the argv vector, where each entry in the argv array corresponds to a character pointer to a string. And since we're only looking for built-in commands, the quit built-in command only consists of one one token. So we're going to go ahead and just look at the first token in argv. So we can do that by looking at argv sub 0, and we want to compare that to quit. And to do that, we're going to use string compare. So string compare quit to argv sub 0. And string compare happens to return 0 if they're the same. And so if in fact quit is equal to argv sub 0, we're going to go ahead and take the easy route and just exit the shell. Okay, so let's go back up now to eval. And for eval, the job's pretty easy. So we can go ahead and check to see if, in this case, the argv that we just parsed is a built-in command. And if so, there's nothing we can do. So, in fact, let me change my condition here. If it's not a built-in command, we're going to do something. And doing something means, in this case, forking and execing a child process. So I'll leave that comment here because I want to test my quit functionality first. So as far as I can see, I have everything in place. I'm parsing my command line. I'm checking to see if it's a built-in command. And if it is a built-in command, that is, it is quit because it's the only built-in command I'm checking for, then I'm going to exit. Okay, so fingers crossed, quit. I try to remake my function. The only problem is it's currently telling me that the bg variable is unused, which is okay because I haven't used it yet. And let's go ahead and test my shell. And it properly quits. If I want to, at this point, I can also do make test02, which remember is the one I failed previously. And it says process built-in quit command, and it works. It quits. It didn't quit before, remember. Okay, so let's do a little bit more. Now that we've finished writing up our quit, or handling our quit command, we're feeling good about ourselves. So let's go ahead and try and deal with this forking and execing of a child process. So to do so, the first thing we're going to have to do, of course, is to actually fork off a child process. And remember, we're going to want to exec the command line given to us within that child process. So in the child process, let's go ahead and, or first let's fork in the parent process. And remember, doing this, checking to see if the fork return value is equal to 0, tells us that within this if clause, we're actually in the child process now. So in the child process, quite simply, we're just going to go ahead and exec. Okay, so we're going to want to, let's use the exec v variant, which means the first thing we're going to have to give it is the path to the command, which happens to be the first argument typed in. And the remainder of the arguments are passed in subsequently as an argument vector. And that's going to be our child process. Our child process is going to be created via this fork, and it's going to exec that program. Okay, so let's try that. Just a little bit of code to start with. And I still get that warning, but we're okay. And let's go ahead and run the tiny shell, and let's try something like binls. Okay, so first of all, we notice that the output is here from ls, and that makes us happy because it looks like the child process properly got forked off and it also execed binls. Notice, however, that the parent process is not waiting for the child to complete because the parent, after all, wasn't told to do so. Okay, I can still type in commands. If I type in binls, or excuse me, binps, notice something that's happened is that the ls command that I exec is now labeled as defunct, which is to say that process is now a zombie process. That shouldn't really surprise you. In fact, if I type in ps now, you'll see the previous ps has also become a zombie process, and these zombie processes are just going to keep piling up because what has happened is that I haven't reaped them. They're not foreground processes. For one, I haven't made them foreground processes in any way. We can see that the prompt got printed out before the output of the children. Okay, and I also haven't reaped them explicitly with a wait. So let's rectify that. So let me quit out of the shell. Quit works now, remember. And let's edit tsh.c again. So at this point, we're not going to do things in necessarily the recommended or the correct way. We're just going to try and hack this together real quick so you can see a very simple approach to getting some things working. So in the child process, I'm doing an exec. And in the parent process, if in fact this is a child process that I've just created, in other words, BG should be false. So if not BG, and I'm in the parent right now. So if not BG, I'm going to have the parent process go ahead and wait for that child process and reap it at the same time. And we only really know how to do both of those things at the same time with a wait system call. And I'm going to hand it a null, which is to say I don't care about the return value of the child process. And remember, this is going on in the parent. So 3 lines of code, or really just 2 lines of code. Let's try making that now. No warning because I'm now using the BG variable. And let's see what happens. So in TSH, bin ls, boom. I have the output, the shell's command prompt comes back to me. If I do a bin ps right now, notice that ls is no longer a zombie process. All seems well and good. Type quit. Let's try test03 now, and that worked. Run a foreground job, it shows me my prompt, it shows me a type quit. All is very good. Now I should point out that our implementation is far from perfect. If I run TSH, what happens if I type in, say, a command that can't be found? Say I maybe misspell ls. Now, things might seem like they're working okay, but in fact, what has actually happened? Well, notice that something sort of odd has happened. Running ps after I ran these 2 commands that should have been misinterpreted. In fact, they should have told me that the command was incorrect or command not found or something. Notice that as a result of those 2 invocations, I now have 2 extra tiny shells running. Actually, it would be these latter 2 tiny shells running. That's very strange. Let me try that again. Let me just try something random. Notice now I have another one. So what happened there? Well, if I quit out of this, oddly enough, it took me 1, 2, 3, 4 quits to get out of this. And if you're confused, I want you to think about this for a little bit. But while you're thinking, let me pull up a val so you can stare at it a bit and think about it some more with the context. So notice what's happening is in the child process that I created, if this exec fails, I'm not currently doing anything to handle that failure. Which is to say, when the child process tries to exec but it fails, it simply goes past this line of code, goes past this BG, and even if it were to execute this wait null, it really wouldn't matter, and then return. And at that point, notice the shell command. The child process is now executing the shell. It returns to the read eval loop. And what's going on now is the child process is reading a command and forking and execing as well. This is clearly not what we want. It's sort of like having recursive shells. So what do we need to do? Well, what we need to do is make sure that we handle the scenario in which exec fails. And it turns out exec returns a negative value when it does fail. And when it does fail, we should just print out something like command not found and exit that child process. Let's give that a whirl. So TSH, that still works. Let's try a command that doesn't exist, command not found, and when we do bin ps, notice no more weird tiny shells being created. And that should be enough to get you started. Good luck.